Yes, yes.
Yes, it is live now. So we can start. Lakshmi.
Let us check, sir, first whether it is coming or not. Sir, okay, madam. Thank you. Let's check, sir, first whether it is coming on.
Okay.
So very good afternoon to one and all present here. So we welcome you all on behalf of South Asian Meteorological Association and SRM Institute of Science and Technology for today's lecture. Now I request Professor Someshwar Das, Secretary, South Asian Meteorological Association, to welcome the panelists as well as the participants. Over to you, sir.
Thank you, Dr. Lakshmi. ABM Professor Tyagi Saab, President of SAMA. Professor Bhaskar Rao, sir, Honorary Professor, Andhra University, Waltair, and member of the advisory panel of the lecture series, and also today's speaker. Members of the organizing committee, Dr. Lakshmi, Dr. Mohan, Dr. Rohini, all the distinguished participants, ladies and gentlemen, we welcome you on behalf of the South Asian Meteorological Association and SRM Institute of Science and Technology, Chennai, India, for this lecture series. As you know, this is the 8th lecture of the series and 4th lecture on atmospheric thermodynamics by Professor Bhaskar Rao. Also, this is the last lecture of atmospheric thermodynamics by Professor Bhaskar Rao. Next week onwards, we shall start the new module in atmospheric radiation. So please be regular and attentive and try to attend all the lectures. So thank you very much once again. Enjoy the lecture. On to you, Dr. Lakshmi Kumar.
Thank you, Professor Someshwar Das, for welcoming the panelists as well as the participants. I think now I can request Professor Bhaskar Rao, sir, to deliver his lecture on thermodynamic diagram. Over to you, sir.
Thank you, Dr. Lakshmi Kumar. Yeah, good afternoon, friends. Today is the 4th lecture in the series and also the final lecture. And it is on the thermodynamic diagrams. That's what, according to the guidelines given to me. So I will be covering the topics on the properties of the thermodynamic properties, energy equivalence in the thermodynamic diagrams, and mostly on the design and application of the thermodynamic diagrams. I will spend more time on the construction of the Tephigram, how it is being developed and formulated. Similarly, Skew-T and log-P thermodynamic diagram, I will spend more time on these two because these two are the most widely used for a very long time. I will also mention about hemogram and the Stu diagram. Hemogram is the first thermodynamic diagram to be developed. Later, other things have come up, but the Tephigram and the Skew-T log-P diagrams are the ones which are in log-P thermodynamic diagram. I will spend more time on these two because these two are the most widely used. The properties of the thermodynamics we can actually categorize as measured properties. That means the parameters which are directly measured, such as temperature, volume, and pressure. And there are some fundamental properties which actually represent the laws of thermodynamics directly. That means entropy, internal energy, Gibbs energy, etc. there are derived properties. That means there are some properties that are derived using through some relations, specific relations between the measured parameters. For example, that means between the measured and fundamental properties, using some specific relations, some properties could be derived, for example, enthalpy and free energy. And to mention among these three, the fundamental properties and the derived properties cannot be measured. Only the some parameters which could be measured and the others have to be derived. The thermodynamic properties are also divided into two general classes: extensive properties. That means basically those that depend on the quantity or size of the matter in a system, in a thermodynamic system. They depend on the quantity or size of the matter, such as mass, volume, internal energy, enthalpy, heat capacity, entropy, etc. And there are intensive properties. That means those that do not depend on the size of the matter or the system, which are, for example, density, pressure, temperature, specific volume, specific entropy, etc. So there are previously also I have mentioned some of these enthalpy as entropy as a extensive property. So there are two broad classifications among the thermodynamic properties: extensive property, which depends on the size of the matter or quantity of the matter, and intensive property, those that do not depend on the quantity or size. And coming to the thermodynamic diagrams, actually thermodynamic diagrams facilitate, and the most important characteristic of the thermodynamic diagrams is that suppose if there is a closed curve that is identified on the thermodynamic diagram, then the area of that particular closed curve and the energy that's being used or absorbed will be directly related to the area. That is the main feature of the thermodynamic diagram. So by looking at the area, you will be able to make some deductions appropriate to the need. So equivalence is one of the main characteristics of the thermodynamics in the application for the weather. Thermodynamic diagrams actually have come into vogue because weather observations are made to understand, because only when you observe the weather parameters, you will be able to understand the characteristics of the evolving weather, so that you will be able to analyze, understand the existing weather and try to make a prediction for the future. So, and when we say, although we live on the surface of the earth, we experience the weather at the surface, that means near the earth's surface where we live. But the weather that is experienced at the surface is related to whatever that is happening throughout the atmosphere and mostly throughout the troposphere. That means the lower strata of the column as enunciated in my first lecture. And typically, the parameters of the variables are the atmospheric parameters such as temperature, wind, humidity, and pressure. And they would be varying both in the horizontal and vertical. And their variation in both in the three dimensions is very much essential to understand the weather situation. We know that radio sound is one of the tools, and observations are made using radio sound balloons. They release the balloons into the atmosphere. I don't actually, but I think Venkatratnam has touched upon the observations of the atmosphere. So radio sound system provides the vertical distribution of some of the atmospheric variables such as temperature, humidity, wind, and pressure, also along with the altitude. So radio sound observations give us the vertical distribution of certain variables like temperature, humidity, wind, and pressure at different heights at a certain location. only at one location, you will be able to see the vertical strata of these, how these variables are distributed in the vertical direction. And these variables give us, if you are able to analyze properly, they will give us a very important information about the nowcasting. Nowcasting means how, if you want to predict how the weather is going to change in the next 3 to 6 hours. So it is one of the valuable tool. These observations provide a very valuable tool for understanding the existing weather as well as for nowcasting. And the vertical profiles of the temperature and humidity very much help us to determine or to predict if there is going to be some cloud evolution, what are going to be the cloud layers, how the vertical motion would be, and if there would be any possible occurrence of the clouds in the next 3 to 6 hours. In meteorology, thermodynamic diagrams are used to analyze what are the measurements that come in from the radiosonde measurements to understand the in situ structure of the atmosphere. On the thermodynamic diagrams, actually, we plot the temperature and humidity at different pressure levels and try to make an analysis and try to interpret them to understand the weather situation. Humidity values are essentially represented by the dew point temperatures, not other parameters such as specific humidity, humidity mixing ratio, relative humidity, etc. So humidity is is represented in the form of dew point temperature. Temperature means dry bulb temperature. We plot both of these two things. You see, from the radiosonde balloon measurements, we get the values at some finite points in the vertical direction, but you can just plot them, these points on the thermodynamic diagrams, and you connect them with a straight line so that you will be able to see the vertical profile of these variables. As I mentioned before, one of the important features of the thermodynamic diagram is the equivalence. And if you observe any closed areas on the diagram, and these closed areas could be directly be interpreted in terms of the released energy or absorbed energy at those levels. You see the enclosed area, find an enclosed area on the thermodynamic diagram. The enclosed area will be can be taken as directly proportion to the energy gained or released. And coming to the thermodynamic diagram, they look complex in the beginning, but it's a very easy to use tool, in my opinion, that facilitates easy assessment of the vertical structure of the atmosphere. In contrast to, you can write down many mathematical equations, try to get them, but instead of doing that, you will see that the thermodynamic diagrams provide us a very easy means to understand the vertical structure of the atmosphere. Even today, despite the availability of many numerical model predictions, etc., thermodynamic diagram analysis is still being used to assess the atmospheric stability at a particular location in order to understand the weather over that particular, especially the atmospheric stability over that location, and also provide some nowcasting in terms of the cloud formation, severe weather, that means any thunderstorm is coming, etc. For the local region. So this thermodynamic diagram is still being used in the local weather centers to make an assessment of the atmospheric stability and also to provide nowcasting. Normally what they do is these are not these radiosonde measurements are being made at only 2 times per day. That means early morning 00 UTC and 12 UTC, so morning 5:30 Indian Standard Time. So at that particular time, you will have the vertical structure, but how to interpret, because normally the thunderstorms in the summer, pre-summer and summer times may be coming in the afternoons where the surface temperature would be very, very high. But what can be used is the weather meteorologists plot these things, thermodynamic diagram, he will put it in the one, then he will try to extrapolate the possible surface temperature variations, because as the day heats up, the surface temperature gets heated up and increases more rapidly. And so what is going to be the surface temperature increase as the day progresses? So at one particular time, when the maximum temperature, like in the afternoon, 13 hours or 14 hours, when you expect the maximum surface temperature to be observed, then what happens is they will try to extrapolate the surface temperature to that value and make an assessment of the possibility of the onset of any severe weather or that particular locality. So thermodynamic diagrams are being used, although they are being prepared only at 2 times. They could be prepared because only 2 times most of the centers release the weather balloons to get these radio sound observations. But these are being used to, by extrapolating some parameters like surface temperature, they do it and interpret. Before going into the design of the thermodynamic diagrams, I will just rush through the entropy. This is a very important concept in the thermodynamics, but most of the physics people should be knowing it. Entropy in a system understood as which is not available for doing the useful work, meaning that it is that portion of the energy that is not converted into work done. That means if the system is working and always some amount of energy cannot be spent, that means all the energy that is available cannot be spent for the work done. And so some of the energy is being left into the system. So that is the entropy. That means this entropy is also related to the temperature. So we will see the entropy change. That means instead of estimating the entropy because it is continuously changing, normally we compute or understand how the entropy change is taking place. So the entropy change ds is equal to dq reversible. That means it is the heat that is being added in a reversible process. So, irreversible process, even adiabatically, a reversible process, adiabatically, irreversible process, you know those things. So, dq or EV is the heat that is being added reversibly to the system at temperature T. So, at temperature T is the temperature of the system, and heat is being added, and then the entropy you can calculate. dq is the difference in the heat. So when a system passes from one state, because we will see in the thermodynamics, the system changing continuously from one particular phase to another, then you can actually see the difference between the 2 states. S2 minus S1 is integral dq by T, and from 1 to 2, that means phase 1 to phase 2. And from the thermodynamics, we know dq is equal to Cp dt minus alpha dp. And that could be written as this equation dq by T is equal to Cp dt by T minus R dp by P. Those things, you know, from the potential temperature definition previously has shown log theta is equal to log T. That means theta is equal to 3 into 1000 by P whole to the power R by Cp. So if you put logarithms on both sides, we will get log theta is equal to log T minus R by Cp into log P plus some constant. So differentiating the previous ones, we will see dq by dt is the same thing which I have written here. And since dq by T is equal to Cp d theta by T, by combining, now we see that Cp, because dq by T is equal to Cp d theta by T, and Cp d theta by T is equal to Cp dt by T minus R dP by P. And so ds is equal to Cp d theta by T, dq is equal to Cp. So previously we know Cp d theta by T is equal to Cp from this one. We know this. So combining the previous one and here we get this ds is equal to Cp into d theta by theta, or the relation between the entropy and the potential temperature now can be written as S is equal to Cp of log theta plus constant. And this is a very important concept which we need to keep in mind when we are dealing with the thermodynamic diagrams, because isentropic process is a very important concept in the thermodynamics. So in an isentropic means entropy is constant. So we see that S is constant means is also dependent on this one. Potential temperature is also constant. So previously we have seen the dry adiabats where theta is constant on a dry adiabat. So dry adiabats are also often referred to as isentropies, and the potential temperature can be used as a proxy to represent entropy of the system. So why I have shown you the small computational exercise is to just show the relation between the entropy and the potential temperature. So, see the entropy and the potential temperature are directly proportional. So potential temperature can be used as a proxy for entropy. That information we are going to use. And before I go to the thermodynamic diagrams, I will just touch upon, maybe most of you are familiar. There are two things. One is equivalent potential temperature. We will be talking about. So if you take an air parcel from the surface and you take it up to the LCL, it becomes saturated. And from the LCL, you take it through a moist or saturated adiabat. That's what we have talked about in the last class. And as the parcel is being lifted above the LFC, condensation lifting level of free convection, LFC, LCL, LFC. So above the LFC, condensation starts taking place. And we see that in this particular one, we are assuming a pseudo adiabatic process. I will tell you what pseudo adiabatic process is just a minute later. And it means that as the water vapor is being condensed above the LFC, it is assumed that all of that condensate is removed as rain and it is not available to any thermodynamic process later. So the equivalent potential temperature is the potential temperature a parcel would have if it is lifted upwards through the pseudo-adiabatic process till all its water vapor is condensed and removed as rain, and then lowered to the 1000 hectopascal level through dry adiabatic process. Because once again, I am saying the parcel with initial at the surface with an initial temperature, you would take it up to the LCL through a dry adiabat. So there is no change up to that. And from the LCL above a little upwards, LFC, level of free convection, from that above, the condensation takes place. And we assume in this particular condition, all the condensate is being removed immediately as rain. So by the time it goes to a certain level, a very high level, there is no water vapor inside the air parcel and it is completely dry. So from that particular level, you bring it to the 1000 hectopascal level through dry adiabat. Then that particular temperature that is noted at the 1000 hectopascal level is the equivalent potential temperature. This is a very important concept, and because it's a conservative quantity during both the dry and the saturated adiabatic process. So I have used the pseudo adiabatic process. It means that it means that it is a process in which the condensed liquid water, that means water vapor is converted to liquid water, and all that condensate liquid water is assumed to be removed. That means it is taken out of the air parcel. It is not available anymore for that parcel. And so that is a pseudo-adiabatic process. So if the water is still available, then if you bring it, then it may again be subjected to warming process. But here, that is not possible. A pseudo-adiabatic process, because in the real atmosphere also what happens is, as the cloud forms, water vapor inside, it is converted in liquid water, and some of it is being converted as rainwater. That means we experience rain. So a part of the condensed water is being taken out as the rainwater. So later this concept will be used when I think cloud physics is being taught. Similarly, contrastingly, there is also a wet bulb potential temperature. It is that the parcel, if it is cooled from an unsaturated parcel, when it is lifted adiabatically from the surface to LCL, that means it is being lifted adiabatically through dry adiabat, and at the LCL, it will be completely saturated. That is our understanding. So take the parcel from the surface to the LCL through dry adiabat, and then from that bring it to 1000 hectopascal level through the saturated adiabat. So not going back, now it is a saturated parcel. So you bring it to the surface or 1000 hectopascal level through a moist adiabat or saturated adiabat. That's what we mean. So this wet bulb potential temperature is a parameter that is a conservative property. That means it does not change when the air mass undergoes an adiabatic process such as adiabatic lift or ascent or descent. So two important concepts I have said: equivalent potential temperature and the wet bulb potential temperature. I'm not going to talk. These two are different. Theta E and theta W are different, and there is a minor difference between these two, but more or less they are noted to be parallel. So with this background, I will just start talking about the Tephigram. As I said, I will talk about two important, because it's a very, very vast subject. I will try to be as concise as possible. I will try to give the fundamentals that is needed for the participants to understand, because some of the students, and then to recapitulate the thermodynamics which they have learned before. So Tephigram is one of the atmospheric four types of thermodynamics which actually are known very well. It is designed as early as 1915 by a British scientist, William Napier Shaw. It was and is being used primarily, mostly in the United Kingdom and Canada. And this thermodynamic diagram has a very important, it satisfies the equivalence, that means the areas and the energies are proportional. So as I said before, the equivalence criteria is satisfied in these diagrams, like the Tephigram, and because they help, unless this equivalence is not satisfied, we will not be able to use it for understanding the CAPE. That means I will also come back to this convective available potential energy a little later. And so the properties of the convective systems can be understood only if there is an equivalence between the closed areas and the energies. The Tephigram is a resourceful tool. It is very easy to use. In the beginning, when you look, it looks very complicated, but I will try to explain to you, show you how it has been designed, then you will appreciate it much better. And it is basically a graph of temperature against entropy. As I said, entropy is being used as one of the coordinates here. And as you know, all the thermodynamic diagrams have their previously, for the physical scientists, they originated based on the concept between a PV diagram, that means pressure and volume diagram, which is very much familiar to all the physicists. So the meteorology physicists have tried to develop, and they have used in this particular Tephigram temperature T and the entropy are used, and the symbol phi is that's why it came into the name phi. T phi gram means it's temperature and the entropy diagram. But later it is being the letter S is being used to represent entropy, because in meteorology phi is used normally used for geopotential. So yes, though S has replaced the symbol, but the Tephigram name is still used as it is. For example, why the thermodynamic diagram? If you just plot T versus Z or pressure, normally we don't get a thermodynamic diagram, because there is no thermodynamic process. Just gives you the temperature decrease with the height. That is the only information we can get from this one. So we need much more of subtle variations of the temperature in the vertical are needed. So see, this is a small diagram. This is the temperature in the y coordinate, and S is the entropy is the x coordinate, and we see A to B is an isothermic process, isothermal process, and the shaded area clearly it denotes dq. That means the heat that is added to the system to keep it. Because the entropy is changing from for the system to be isothermal, that means to keep the temperature constant. So some energy is being added or depleted. That particular, this area denotes that. In a T and temperature entropy diagram, this is a simple concept. dq, that means the heat added, is equal to T into ds. ds is the change in the entropy that is denoted on the x-axis. For example, I will tell you the steps how the design has been initiated. So we see here on the x-axis S, as I said before, theta, the potential temperature, could be used as a proxy to the entropy. So this theta 1, theta 2, theta 3 increasing in the x in this direction, x direction. Theta is increasing here. Similarly, y-axis shows temperature T1, T2, T3, T4 is increasing in this direction. And also some pressure lines have been plotted here, slanting across from left bottom to right top. So the slanting green lines are the isobarts, and P1 pressure is increasing from here to here. P2 is greater than P1, P3 is greater than P2. So this is the first design that went through. Then the next step is they have rotated this diagram through 45 degrees, so that T and theta lines slope across this is a slope. The entire diagram shown in the step 1 is rotated 45 degrees anti-clockwise, and so you have the diagram just rotated. And then this is an important step. The whole of the diagram is now reflected about the s-axis. So here the s-axis is here. The x-axis, s-axis, entropy axis is here. Now I say that the whole of this is reflected. So S is still here on this side, and whatever that here, this got reversed. The whole of the P lines also get reversed. So we have the entropy, or the theta 1, theta 2, theta 3, theta 4 here. As I said, so theta 1 to theta 2, theta 3, theta 4 is increasing. T1 to D4 is increasing. P1 to P2 to P3 is increasing. So, but here when you see this particular diagram, see P3 is greater than P2, P2 is greater than P1. So if you see this diagram, if you go from bottom to top, the pressure is decreasing, which is what happens in the atmosphere. And if you see the temperature, T4 is here at the bottom, T3 is less, T2 is less, T1 is less. So if you see the temperature also, as you go up, the temperature is decreasing, as that happens in the real atmosphere. And here, if you see the potential temperature, it is theta1, theta2, theta3, theta4. So theta4, theta1 to theta4 is increasing. And that is the distribution of the potential temperature in the atmosphere also. The observed potential temperature shows increase with height. So at this particular stage, the thermodynamic diagram will have a representation of the pressures decreasing from bottom to top and the temperatures increasing from bottom to top, temperatures decreasing from bottom to top, and the potential temperatures increasing from bottom to top as we see in the atmosphere. So these three variations resembles their pattern in the atmosphere. Well, that is the background, and now I will just show you the Tephigram as we use it. And there are only two lines apart from the isobars, isotherms, and the isentropies. We have two lines. One is the water vapor humidity mixing ratio. It is the humidity mixing ratio is the dashed lines running from bottom left. So here you have the dashed lines running from bottom left to right top. So they are also being represented in terms of grams per kilogram, and they will denote the humidity. And the other one is the equivalent, constant equivalent potential temperature. I have defined and I have explained you the concept of the equivalent potential temperature. These lines are nearly vertical here, but they slope towards top left corner as we go up. As the pressure decreases, they go up and then become parallel to the Adiabatics. So altogether, we have the isotherms, isobars, then isentropies, that means Adiabatics. Theta lines are also Adiabatics, and then now we have the water vapor mixing ratio lines, and we have the equivalent potential temperature lines. Well, at the beginning, this diagram may look complicated. Once again, I want to show you these thick lines are the isolance pressure. They are horizontal, and as you go up, the pressure decreases. These lines, the pressure decreases from bottom to top. And these lines, the sloping lines are the isotherms, and 0 degrees centigrade one is dashed. Just to illustrate in a black and white diagram to make it more clear, I have shown you this. These dry adiabats, these are the lines which slope, straight lines which slope from bottom right to top left. These are the adiabat, dry adiabats are the lines of the constant potential temperature. And these are the curves which go up and slightly slant towards top left, or the equivalent potential temperature lines. And these are the dashed lines are the humidity mixing ratio, water vapor mixing ratio lines. They slant slowly from bottom left to top right. So once again, just to make it clear, I have shown you. These are the things anyway. Again, these 4-5 things have done. The isobars are the near horizontal lines here. And isotherms, these are the red lines, is the isotherms. This dashed blue line is isobar. And dry adiabats, this brown color line is the isobar. And the saturated adiabat line is this one. This is also theta E, or the saturated adiabat line is this one. And this one is the humidity mixing ratio line. So these are the basic lines we have on the Tephigram. I have taken a little more time probably needed because just to make sure you got the information on the lines very clearly. So a radiosonde, when you plot the temperature and the dew point, so this red curve is dry bulb temperature, the blue one is the dew point temperature. As I said, the humidity is being converted into dew point and is plotted here. So the blue line shows the dew point temperature, the red line is the dry bulb temperature, and its variation with height in terms of the pressure is being plotted. And this shows on a typical day, if you have like this, normally the gap between the temperature red and blue, the temperature and dew point will give you an idea about the humidity of the air. That means if they are closer, the humidity is higher. If the gap is wider, in those layers where the gap is larger, the air is supposed to be drier. So a small gap means more moist, a larger gap, that means the distance between the red and the blue, or the temperature and the dew point, denotes a drier air, and a smaller gap indicates some moisture, more humid air. And here you see the dew point curve crosses the 850 here, and this is the 3 grams per kilogram curve. That means at that particular level, the air contains 3 grams of water vapor in a kilogram of dry air. And apart from this, we know that these arrows, they represent the wind structure. That means the arrow gives you the direction from which the wind is blowing, and the shafts indicate the magnitude. The shafts indicate the magnitude of the wind. That means the speed and direction are being represented here, are plotted as wind barbs. That is what we call. And the arrow shows the direction from which the wind is blowing. That means, and putting the 360 degrees, if it is pointing upward, pointing 12 in a clock, that's a true north. And if it is pointing to 3 in the clock, it is east direction. And if it is 6, then it is southern direction. If it is 9, it is a western direction. So that is how we look at the one. So the wind direction is being plotted. So it is now here between the east and south. So the direction of the wind is southeast. And the number of barbs they represent, a longer barb is 10 knots, and half of it is 5. So that's how the wind speed and direction are being plotted. So it gives us the wind properties also. Most of the times we need the vertical wind shear in order to interpret certain weather systems. So we will see how to use this Tephigram to calculate the lifting condensation level. Previously also I have explained the lifting condensation level is the level at which the air parcel attains saturation. So now on the Tephigram, we have the lines of constant potential temperature theta are also the same. They are also called the adiabatic lapse rates. And so what we do is, here, for example, T is the temperature value, that is an observation. TD is the dew point temperature, that's a representation of the humidity. So these are the observations that are taken from the radiosonde observation. They are plotted at the pressure level. They're like 1000 hectopascal on this diagram. So this dot represents T, this dot represents dew point temperature. Now what we do from this T, we follow the dry adiabat. So what you do is, from here you follow the dry adiabat. The red arrow shows it is following the dry adiabat. So you follow upwards through the dry adiabat, which is being shown here, red arrow. and the TD is the dew point temperature. It follows the humidity mixing ratio because along the humidity mixing ratio line, the humidity mixing ratio is constant. That means the water vapor content does not change. So from the TD, this point, you follow the humidity mixing ratio line. So as you go up, this blue line is being shown. The point where these two intersect, that means we are following the dry adiabat through the dry bulb temperature value at the 1000 hectopascal and the humidity mixing ratio line through the TD value from the 1000, and the point where these two lines intersect, that is the level where the parcel attains the saturation. And also we know conceptually that it is the lifting condensation level. So from the definition and what we have learned before, we can very easily use the Tephigram in order to get the LCL. So here I have shown you how to get the LCL on the Tephigram. For example, if you have the air parcel here, then what you can do is you can also derive the properties at the 1000 hectopascal. So you simply follow from this particular point the dry adiabat and come to the level where you need, and you will get the temperature at that particular level, dry bulb temperature at that particular level. So if this is the LCL, follow downwards the dry adiabat to the level you go, and that particular point which intersects the pressure level where you need 850 hectopascal in this case, you will get the dry adiabat value. Similarly, you follow the humidity mixing ratio value, come to the 850, and you will get the TD value. So reversibly also, I have shown you, I have explained to how to get the LCL, but in the reverse also, from the LCL, you can derive the values of the T and the TD at different levels below. This is a very useful exercise. And I gave you the explanation. I gave you the definition of the wet bulb potential temperature. It is the temperature, it is the potential temperature that the parcel would have if you take the parcel from the LCL, bring it to the level of 1000 hectopascal following a saturated adiabat. So here, what we did from here, it is the value of the dry bulb temperature, or for example, and this is the dew point. So from here you go, follow the dew point through the mixing ratio line, follow the temperature through the dry adiabat, and the point of intersection is LCL, as we know. From that particular point, bring the parcel through a saturated adiabat to the 1000 hectopascal level. That will give you the wet bulb potential temperature. As explained to you before, the wet bulb potential temperature is a conservative property. It is useful to understand the characteristics of the atmosphere, because potential temperature is a conservative property, wet bulb potential temperature is a conservative property. Similarly, equivalent potential temperature also is a conservative property. Well, I will just show you and explain with the Tephigram. For example, this is the environment curve. This orange one is the environment curve. So if you have the surface, what we do is the parcel is being taken upwards dry adiabatically till its saturation, that is the LCL, and above the LCL it follows the saturated adiabat. So this is the curve that goes from surface to LCL through dry adiabat and through above that. And in all these things, the parcel is cooler than the environment curve. So that means the atmosphere is absolutely stable. So because the parcel, whatever the process you give any lift, wherever you take the parcel, any height above, then it is still cooler than the environment. So it is always stable. And here, if you see, this is the environment curve, the red one. And now we follow the parcel from here through dry Adiabatic. So here the TD is here, the blue dashed line, these two meet here. So this is the LCL, and above LCL, the parcel follows the saturated Adiabatic upwards. And here you see, and here up to this is actually the level of free convection. Up to this parcel, sorry. So here, the parcel right from the beginning, it is warmer than the environment. So from this particular point to this particular point, the parcel is always unstable. So the atmosphere is unstable right from the surface to this particular level till this parcel becomes neutral here and then is cooler than the environment. So if you see, this is the environment curve, and the lapse rate of the environment is far steeper than the adiabatic lapse rate. And so the parcel which is being taken up from the surface, it is warmer than the environment. Up to this particular level, it is warmer than the environment. So from here to here, it is unstable. And above that, it is stable. So the area here, it is an unstable area. This is a negative. This is a negative area. This is a positive area. We will talk about that later. And coming here to conditional instability, and here this red curve is again the environment curve. So following the same procedure from the surface to the LCL. So the red one is from the curve from the dew point temperature following the humidity mixing ratio, and the dry adiabatic, the dry bulk temperature. Here the LCL is there. And still you go up from here, it follows the saturated adiabatic, and this is the level from which because condensation takes place and the parcel is buoyant. That means the parcel temperature is higher than the environment. And the parcel, sorry. The parcel temperature is warmer than the environment. So from this particular level to this particular level, this dashed line, and so this between these two levels, it is unstable. And from the surface to the LFC, it is stable. And this is a representation of the conditional instability of the atmosphere shown on a Tephigram. So some examples of the Tephigram I try to give you, and maybe now I will go to the Skew-T and log P diagram. It is actually most commonly used in the United States. In 1947, scientist by Herlofsson, he modified the hemagram. I have not touched about the hemagram. I will tell you very soon. I will touch upon the hemagram also. This has straight horizontal isobars, and with a little angle between the isotherms and dry adiabatics. And it is Skew-T is because the temperature is slightly skewed. That's why it got skewed T, and the y-axis is shown on as pressure, not linear pressure, but logarithm of pressure. So the variation on the y coordinate is being represented logarithm of the pressure values. So it is a skewed T. T is the x-axis. Y-axis is P, but it's a log P, and the temperature lines are not purely vertical, but they have slight inclination, slightly skewed. That's why they are called Skew-T log P diagram, and mostly it is referred as only Skew-T diagram. And this diagram is like the Tephigram is very much used in the United States even today for the analysis of the radius on vertical profiles of the temperature and humidity, and for making some local weather predictions. In this diagram, the isotherms are slightly slanted, they're skewed, as I said. Isobars are lines of equal pressure. And here you see, this is much better. So the horizontal x-axis is temperature given in the degrees, and y-axis is P, but a logarithm of P. And so these isobars are straight horizontal lines, but the isotherms are not exactly perpendicular to the isobars, but they are slightly slanted to the top right. And so that's why it is shown. So these lines are isotherms, these lines are the isobars on the Skew-T diagram. Next, we will show you there is isohums, means humidity mixing ratio lines, grams per kilogram. These blue dotted vertical lines, almost vertical but slightly slanted towards the right, they are the isohums, or the lines of equal humidity mixing ratio. Next, the dry adiabats, as you see, theta is potential temperature, lines of equal theta or the dry adiabat are shown here. These brown lines, which actually slant from top left to right bottom. So they are slanting here, a little concave in the curvature. The solid lines that run from top right to bottom left. And the theta is being shown here. So isobars, isotherms, to start with, added isohums, dry adiabats are added. And now we add the moist adiabat or the saturated adiabat. These are the lines which are shown here, brown dotted ones. And so these are mostly vertical, but they slant and become parallel to the dry adiabat at higher levels, because the water vapor content is nearly zero at those levels. So they become mostly parallel to the dry adiabats. And these lines are also called theta E or theta W, as I was said in the definition of the equivalent potential temperature. So a complete form of the Skew-T diagram, we see here the isobars here, the isotherms slanting, slightly slanting here, these lines. Then the isohums, these blue dotted lines, and the moist adiabat, the brown shape, the broken lines, and the dry adiabat is the solid line, brown line extending from top left to the bottom one, just all of them put together. And on the Skew-T log P diagram also, we can see how we can get the lifting condensation level. So a parcel at this pressure, at this same pressure level, it has the temperature T, it has the dew point temperature TD. And so here, as I said, what we need to do is follow the dry adiabat along the dry bulk temperature, that means T. Follow the dry adiabat from the T, and follow the humidity mixing ratio line through TD. And we see here, and from the surface or the level where which we started, we followed the dry adiabat from the surface. We go up to a certain level from the TD along the humidity mixing ratio line, and the point of intersection, or the level of the intersection, is called lifting condensation level. That means that's the level at which the parcel gets saturated. And above this level, normally we take the parcel along the saturated adiabat. So from here, the parcel does not follow the dry adiabat, but it follows the saturated adiabat. This is how we can obtain the lifting condensation level on the Skew-T log P diagram. And previously, I have talked about the level of free convection. That is, above the LCL, the parcel still needs a lift till the condensation starts. Unless the condensation starts, there is no heat release within the parcel, and the parcel would not get buoyant. But so there is a level of free convection. It is the level at which actually the parcel becomes buoyant. That means the temperature of the parcel becomes will be more than the environment from that particular level. If you see here, this the T and this the TD, and you go to a point here. So the follow the humidity mixing ratio from here to here. T Adiabatic, this is the level the saturation, or it is called LCL. And from here, as I said, the parcel will follow the saturated adiabatic, but only at the LFC. Only at the LFC. Above the LFC, the parcel is warmer. The parcel, because the same saturated adiabatic, if you follow this, the parcel is warmer from the LFC up to another level where it becomes has the neutral buoyancy, or the temperature of the parcel will become equal to that of the environment. So between LFC, so I have noted down here the LFC, it is the level, lifting condensation level, or the level at which the parcel attains saturation, or they follow the parcel from the surface through the adiabatic, and they follow the TD through the humidity mixing ratio line at which they intersected the LCL. Above the LCL, you have to follow the parcel through the saturated adiabatic, and at certain level where the parcel becomes starts condensing and becomes warmer than the environment, that is the level of free convection. And again, the parcel above that, as it goes up, at some level, it will become neutral. That means the temperature of the parcel will be equal, and above that, the parcel is cooler again. The parcel is cooler again. So here we note down the LFC, and we note down the EL. EL is EL is the equilibrium level. You can read here, but I am just explaining. EL is the equilibrium level, that is the level of neutral buoyancy. That means the parcel temperature and the environment temperature become same, and above which you will have the parcel to be cooler again than the environment. So between the LFC and the EL, we have the positive area. That is what we call, that means the buoyant energy, buoyancy of the parcel is very high, or the kinetic energy of the parcel is very, very high between LFC and the EL, means equilibrium level. And below the LFC, there is a negative area. That means, I will explain to you, that means that is the energy that is needed for the parcel to be lifted from the surface to LFC. So the negative area represents, later I will talk to you about these positive and negative areas. So at this time, please remember this, the positive area, this is the negative area. The negative area is the area between the surface and the LFC, level of free convection. The positive area is the area between, enclosed by the curves of the environment and the air parcel between the LFC and the equilibrium level. So this is how we identify. And now I will talk a little about the convective available potential energy. Actually, convective available potential is a measure of the amount of energy available for convection. That means if a convection has to take place, we need some amount of energy available. And in the upper sounding, as I have just shown you here, and there is a positive area. Positive area is identified. This positive area is actually represents the amount of energy that is available for convection, or the kinetic energy that is being required. And CAPE means convective available potential, acronym for that. And it is joules per kilogram. It is CAPE is actually a measure of the buoyant energy of a parcel, or the kinetic energy of a parcel, and which also denotes the updraft intensity inside the air parcel between the LFC and the equilibrium level. And it also denotes the a potential for the formation of severe convection such as thunderstorm. So CAP is one parameter which is being dealt with by the weather forecasters on any day. Mathematical expression can be written. It is the integral of RD. RD is the gas constant, and TV is the virtual temperature of the parcel minus virtual temperature of the environment integrated between two levels. That is the PN is the level of free convection. PF is the level of free convection. PN is the level of the neutral buoyancy or the equilibrium level. As I said, it is the area between, because we are doing with a D log P in the P scale, we have to make the integration downwards. So PN is the level of the neutral buoyancy that represent the equilibrium level. PF is the pressure at level of free convection. So Kp is the difference. It is dependent on the difference between the virtual temperature of the parcel and the virtual temperature of the environment. The larger is the virtual temperature of the parcel, the higher buoyancy it has. And here we have seen the positive area and the negative area. So CAP or the Cape represents the positive area. That means the energy that is available, positive energy that is available for the parcel are generated in the parcel. So greater is the Cape, convective available potential energy. Greater is the potential for severe weather such as thunderstorm. So it's the concept of Cape is very, very important in the thermodynamics. Convective inhibition, it is the energy that is needed to lift the air parcel upward from the surface up to the LCL, and then up to the LCL through dry adiabatic process, and then through a saturated adiabatic process from the LCL to the level of free convection. So sin denotes the energy that is to be given to the parcel, because we said there is a need for the parcel to be given energy to lift it up from the surface to the level of free convection. And sin is a convective inhibition, and the formula is given as RD TVP minus TVE minus is given just to denote it is the negative energy that we are talking about. And PF is again the level of free convection, and PI is the level at which the parcel originates, normally 1000 hectopascal or surface, whatever it is. So PF is the level of the free convection, PI is the level of the origination. So sin is purely represents the energy that is needed to lift the parcel from surface or wherever it originates to the level of free convection. So the higher is the sin, the greater is it inhibits the formation of severe weather like a thunderstorm. The higher is the Cape, it actually helps the formation of a thunderstorm, cloud, etc. But sin that means the convective inhibition acts as a cap on the convection, and but if the lift is stronger, and if it can go through, if any air parcel can be lifted through the sin above, then normally suddenly it actually helps the formation of severe convection. That means the sin is stronger, it means it's a cap on the convection, it's a constraint on the convection. But if you have stronger support, if the parcel can go beyond, then the Cape the energy can be fully realized, leading to the formation of convection in the atmosphere. Here I am showing two small examples, one on the Tephigram, one on the Tephigram. Here you can see a parcel that is going on. The red line is the environment, and the black line is the one which we there is a crosstalk. I don't know what it is. Here, this is the negative part of the energy. This is the positive part of the energy. So CAPE is high in this particular case, as we see. This is the line for the TD, and this is the line for the T line. And so the parcel which is going, it is going through the level. So this particular part, this is the level of free convection here, and this is the negative energy, this is the positive energy. Similarly, it is on a Skew-T diagram, as we see. This is the LCL, this is the LFC, and so this particular area is the SIN, and this particular area is CAPE. In both cases, CAPE is much larger than the SIN and indicates stronger convection to occur. And I will just a few more minutes, kindly bear with me. And as I said, there are two other diagrams like emagram. Emagram is actually the first atmospheric thermodynamic diagram that was devised as early as 1884 by Heinrich Hertz. And it stands for energy per unit mass diagram. And in the beginning, it was essentially used in the European countries. As you see, the temperature lines are in the emagram, the temperature lines and the pressure lines. Pressure is logarithm of P on this one, but it is the pure temperature is plotted on the x-axis. These temperature lines are almost vertical, the pressure lines are horizontal. So actually the isobots and isotherms are perpendicular to each other in this. And the brown one, we have the dry adiabat, we have the moist adiabat, the thick dasher lines, and we also have the humidity mixing ratio lines, isohumes. This is the basic pattern of the emagram, but actually the Skew-T log P diagram is a revised version of the emagram, and then the Americans started using the same thing as a thermodynamic diagram. So Skew-T log P diagram is a revised version of the emagram. Emagram is the first thermodynamic diagram to say that, and later offshoots are Skew-T log P, and Tephigram has been similar to emagram, but it has been separately designed by the Britishers. And there is another diagram called a Stu diagram. It was developed in around 1927 by George Stu, and it was very widely used because it is very used. Most of these lines are perpendicular to each other, and most of them are straight, except that the moist adiabat lapse rate. Most of them are very straight, except for the moist adiabat, and isohumes are also almost straight, but a little slanted. The only deficiency in this two diagram is that the energy equivalence is not satisfied in this one. So it may give you an idea about the vertical structure of the atmosphere, how the pressure, temperature, and humidity are related. But if you find something on this two diagram, it may not give you the area may not, because unlike in the Tephigram and the Skew-T log P diagram, where the area, positive area, denotes the energy that is available, or the energy that needs to be given. So those areas equivalence is not there on this two diagram. So it's not being used widely now. Anyway, pressure decrease is being given according to the P by P0. I think this is what all I wanted to say as far as atmospheric thermodynamic diagrams are concerned. It is a very, very vast topic. The students have to spend more time putting the thermodynamic diagram before them, and then try to plot, and then try to understand the situation I have shown you. Given the time, or feeling the time that is available to me, I try to give the rudiments of the thermodynamic diagrams, especially I have spent more time on the Tephigram and the Skew-T log P because they are the most widely used Tephigrams as on today. But I gave you some information about the hemagram and the Stuve diagram also. I think I am ready to give any more information that is required, but this is the best I could do within the time limit I have. Thank you very much for patiently listening to me. I am ready to answer any, give any clarifications. Thank you.
Thank you very much, Bhaskar Rao, sir. So for your wonderful talk. See, now it's time for question and answer sessions. I request Dr. Rohini and Dr. Swagata to take care of this session.
Thank you, sir, for such a nice lecture. There are a few questions. So the first one is, Professor could elaborate a little bit on thermodynamic properties. Which one of intensive or extensive properties depends on the nature of matter, but do not depends on the quantity of matter? I mean, the intermolecular force of attraction and intermolecular spaces. And how do they behave under different conditions like pressure and temperature?
Yeah, I think they should go back to this. The fundamentals of that I have given the broad classification according to the extensive and the intensive properties. They mostly depend on the volume and size of the thermodynamic system we are considering. So it is much going deeper into the molecular attraction between that. I think that's not the scope of my talk. At least I cannot answer that at this time.
Okay. Sir, another question is, what is the difference between Skew-T and T5 diagram?
Yeah, there is a minor difference between the organization of that. I have not given the equations which go into the construction of these 5 elements like the isobots, isotherms, diadiabat, why they should be in that particular orientation. I have not given the equations because if I start writing down the equations for each of these one, they are very much similar, but there are slight differences which they can notice. The Skew-T, essentially the Tephigram has the theta as the vertical axis on the x-axis, whereas the temperatures are directly plotted as x-axis on the Skew-T log P diagram. And accordingly, there are some minor differences do exist between the curves that are there, the dry adiabat, the moist adiabat, and the isohumes that are related to because the temperature and humidity are related to them. So there is a minor variation because the x-axis is different, entropy or the theta or what is there in the Tephigram, and T is directly given on the Skew-T log P diagram.
There is another question. First, they would like to thank you for the informative talk. The question is there any threshold value of K above which always it indicates severe thunderstorm?
Yeah, I have not touched because application and there is about 1,000-1,500 joules per kilogram of CAPE always helps because that varies from region to region, but around 1,000 to 1,500 is a very good threshold, but there is nothing like 900, 950. I should not say that. The higher the CAPE, higher it is more favorable. When the sin is very, very small, even some value of the significant value of the CAPE would lead to convection. If the sin is very large, even if you have a larger value of the CAPE, it may not actually lead to good convection. So you have to make an analysis of both the sin and CAPE, and then try to assess the situation, and then try to make an assessment whether that particular condition would lead to convection or not.
Dr. Swagata, would you like to take over?
No, Rain, you continue.
Okay. Sir, another Question is, let me know if Tephigram is manual graph or model output. Tephigram is manual graph or model output.
It's not model output, no.
Yeah, it is a manual graph.
Absolutely.
Another one is, what is impact and consequences of climate change variability and greenhouse gas emission on Cape for the entire atmosphere?
I think that's a very absolutely different topic. We are just talking about the thermodynamics of the atmosphere, thermodynamic diagrams. I had to talk more, make some assumptions, how the temperatures would be, how the lapse rates would be, how the temperatures are above. But the only thing is in the global warming scenario, we see that more severe thunderstorms are being experienced. Only to that, because it is too much for me to elaborate the global warming, the increase of the greenhouse gases. It is not the right turf to grope about at this time.
Yeah, I think those are the questions. One was like, please can you explain Tephigram with a plotting exercise? But I think you did it, sir. You showed one.
Yeah, it should. Everybody should go. Actually, I know how to construct the Tephigram, how to write these equations, but I thought it is beyond the scope of that, because this is something like introducing the concepts of thermodynamics, thermodynamic diagrams. If I start writing down the equations, I think that would mask the essential scientific aspects. So I did not touch or go into that. Somebody who is interested, I can provide the information. They can actually go through that. As a student of meteorology, in my MSc, we have written down the equation. We were building up the moist adabate, dry adabates, everything in the classroom. That took about 6 months. I don't know whether Someshwar Das did that in his MSc, but we did as a student in 1966, 69. I very much remember every day doing this exercise, how to construct these various these five of these parameters. That's a big exercise.
Sir, we have provided your email, so I'm sure that you are going to get lots of emails. So, yeah, thank you, and over to you, Dr. Lakshmi.
Thank you, Dr. Rohini and Dr. Swagata. And I thank Professor D.V. Bhaskar Rao, sir, for completing fantastic 4 lectures in atmospheric thermodynamics. So in these 4 lectures, we have covered main topics such as structure of the atmosphere and vertical distribution of temperature, pressure distribution, atmospheric stability, and today, so we have completed thermodynamic diagrams. So with this, the sub-module of this atmospheric physics module has completed. So on behalf of SAMA and SRM, we thank Professor D.V. Rao for his wonderful lectures. And next week, we will have a new sub-module will start. So that is on atmospheric radiation. So in the module of atmospheric radiation, again, we have 4 lectures, 4 weeks. So the first lecture, that is lecture 9 in the serial number, it will be on laws of radiation, radiation budget. And second lecture, that is on week 10, we have greenhouse effect. Week 11 and third lecture, scattering concepts. So that involves size parameter, concept of Rayleigh and Lorentz scattering. And week 12, the lecture 4 of atmospheric radiation will be on radiative transfer. That is general equation, plane parallel equations, and atmospheric solar heating and cooling rates. These are the 4 lectures will be covered in the coming submodule. So an important instruction to be participants note. So due to some speakers unavailability, so we will not be conducting the next week talk on Saturday. Instead of Saturday, we will be conducting on March 6th. We will send an email on this. So next Saturday, we will not have a talk. It will be on Monday. So that is March. Instead of March 4th March, we'll have a talk on 6th March. Participants, please note down this. Instead of 4th March, we'll have talk. That is first lecture on atmospheric radiation will be on 6th March, that is on Monday at 3 p.m. IST
Instead of
or 9:30 a.m. UTC we will have. We will send an email on that. We will send a reminder also on that. So I request you, all the participants, to attend the talk on 6th March. So afterward, the lectures will be on, as usual, on Saturdays. Only next week lecture will be on next Monday, not on Saturday. Okay, I hope please note down this one. So with this, I request Dr. Mohan. Before that, we will have one photo session.
Yeah, I think so.
And since we are completing thermodynamics module, I may request Tyagi sir or Someshwar sir to make remarks. Sorry, this is not in agenda since we are completing 4 lectures in atmospheric thermodynamics. So anything you want to tell sir, Tyagi sir and Someshwar sir, you can.
Tyagi sir will say.
You can.
Tyagi sir, आपका mic mute है.
Yeah, thank you, Lakshmi. Well, words felt to express our gratitude to Professor Bhaskar Rao for taking this first 4 set of lectures. It's a beginning of very important initiative of the SAMA, and he has been a guiding spirit and taken a lead to deliver these 4 lectures on a very important topic and very insightful, informative overview of the atmospheric thermodynamics. With his vast experience, he has covered to the point within the available short time, and as suggested that those who have some more clarification they need, I think he'll be too happy to respond to them. Also, in question answer session also he has responded, but otherwise also I request him to respond to the.
I'll be very happy, sir.
Thank you, sir, and thank you so much. Lakshmi also may take your help to set some questions for the candidates who want to appear in the grading system which we propose to have. So thank you so much, sir, and we continue to have your guidance for the following lectures also, as and when you feel like that we need to modulate or we need to do, so we will take your help. Thank you so much for your available time, sir. Thank you, sir.
Thank you, Tyagi sir. Someshwar, you want to tell anything in brief?
It's okay. Everything has been said by Tyagi sir, but really we are grateful to Professor Bhaskar Rao sir, and all the participants feel privileged to hear these lectures from a person like Professor Bhaskar Rao, who has been the teacher of hundreds of students under him. So many students have already done the PhD, and they are at all very high positions at different places, not only in India, but also abroad. So it's really a privilege to all of you, all the participants, that you have heard the lecture from such a privileged person, great person. So all the best, and please do continue to attend all lectures. Please be regular. Some of the people are asking about the video. They are all available on the YouTube, and they will remain available. You can watch as many times as you want. No problem at all. Okay, so that's it from my side. Thank you very much, sir, once again.
I want to say a few words before it closes. I am very much thankful to SAMA, especially Professor Tyagi ji and Professor Someshwar Das, for giving me this opportunity to deliver these 4 lectures, for their confidence in me, and for asking me to do this. In fact, this has been a very good experience for me once again to recapitulate whatever I have learned and whatever I have taught before, and coming back to great audience of the South Asia Meteorological Association, coming before them, and then try to share the information with the young people. I feel very, very happy and feel honored that SAMA asked me to do this job. I will be very, very happy to do teaching at any time, because that's my passion, and I will be very, very happy. I will definitely follow these lectures, because I will participate, attend to learn myself, whatever that is in the next 2 modules also on the atmospheric radiation and cloud physics. I will definitely be attending. It would be my privilege to participate and learn Thank you very much once again to SAMA, Professor Tyagi, Professor Sumeshwar Das, and for the assistance rendered by Dr. Lakshmi Kumar, Dr. Rohini, and all other people who have helped me to deliver these lectures as per the schedule. Thank you very much. I feel honored and privileged.
Thank you, sir.
Thank you, sir.
Now we will have a formal photo session. I request all the panelists to turn on their videos. Sagada, please turn on your video. Oh, it's video on, sorry. Okay, thank you. Now I request Dr. Mohan Das to deliver the vote of thanks.
Distinguished guest, esteemed resource person, esteemed members of the coordination committee, and dear participants. It is with great pleasure and honor that I stand before you to express my sincere appreciation and gratitude for the successful completion of today's international lecture series session on atmospheric physics, atmospheric thermodynamics, and thermodynamic diagram. That is the end of this submodule. I would like to extend my heartfelt gratitude to our esteemed speaker, Professor Dr. Venkata Bhaskar Rao sir, who is the Honorary Professor of Department of Meteorology and Oceanography, Andhra University, India. Your enlightening and informative speech has left an indelible impression on us all, and we thank you for sharing your invaluable knowledge and expertise with us. I'm confident that your content has provided us with a new perspective on atmospheric physics and has inspired us to pursue further research in this field. I would like to express my sincere appreciation to the respected members of the Coordination Committee of SAMA's training course, including Air Vice Marshal Retired Professor Dr. Tyagi sir, who is the President of SAMA, Professor Dr. Someshwar Das sir, who is the Secretary General of SAMA, Dr. T.V. Lakshmi Kumar, SRM IST and Session Moderator, Dr. Rohini Bhawar, SPPU India, Dr. Akhilesh Mishra, NCM RWF India, Dr. Swagata Paira, BRT Mesra India, and board directors and organizing committee for their tireless efforts in organizing this highly effective training program. Your dedication and hard work have made this program a resounding success. Last but not least, I would like to express my gratitude to all participants from SAMA countries and beyond for your enthusiastic participation and engagement throughout the program. Your active involvement has contributed significantly to the success of this event, and we hope that you will continue to collaborate and share knowledge in the future. Once again, I extend my sincere gratitude to all those who have contributed to the success of this event. Thank you.
Thank you, Dr. Mohan, for delivering the vote of thanks. So with this, I think we can conclude the session. So I request all the participants, they may leave the webinar room. So thanks very much. So we will be meeting on 6th March, 3 p.m. IST, 9:30 a.m. UTC on the module for atmospheric radiation. Thank you very much, all of you.
Thank you.
Bye-bye.
Thank you.